Hi, this video covers the structure of the chained hash table and how its operations work. So before we can get into the concrete details of how a hash table data structure works, we have to define some kind of collision resolution strategy. Remember that hash collisions can happen. It's just a fact of life with hash functions. A universal hash function family is one where the probability of a collision is small. It's only 1 over m. M is the size of the vector that we're using, so the hash codes or hash values are 0 through m minus 1. For example, multiplicative hashing that we covered in a previous video. So collisions are unlikely there, but they're still possible. It's a non-zero probability. So any viable hash table data structure needs to somehow deal with collisions, and that's kind of the last aspect of hash tables that we haven't covered, is how do you deal with that? A collision resolution strategy is the approach that a hash table data structure uses for handling collisions when they do occur. And there's a number of them that have been developed over the years. One is chaining. So in chaining, V of hash of key is a singly linked list of all the colliding pairs. So rather than just having a pointer to one pair there, we have a linked list of perhaps one or maybe more than one pairs that all collided according to the hash function. Another alternative is called linear probing. So there, each element of the table is just a pointer to a single pair, and if V hash of key is taken, if something is there already due to a collision, then just try the next index up, and if that one's taken, try the next one up after that. Cuckoo hashing is a different idea. There you have kind of like a backup vector called B. So if you try to insert into V at hash of key, but that's taken due to a collision, then try B, the backup table. And there's others. This video is going to cover the chaining approach. So here's how a chained hash table works. What a hash table has is the table. So the table is a vector of m singly linked lists of pairs. That's kind of the main part of the data structure. And we would declare that as a vector of singly linked list of pair kv. So kind of a complicated declaration there, but the idea is you've got this vector called the table. It has m elements for an appropriate choice of m, and every element of that vector is a singly linked list of pairs. Often many of those lists are just empty, they don't have anything in them. A lot of those linked lists only have one pair, but it's a list because there's a possibility of a collision. So this list here with two pairs in it would have arisen when we had two separate pairs, 94 and 87. If those two keys collide and map to the same index, then the way we handle that collision is we just have two elements in that singly linked list. So we call that linked list a chain sometimes. M is the length of that vector, and we maintain M to be reasonable, and concretely we'll maintain that N is less than or equal to M. So M, the size of this vector, is always bigger than the number of elements, or maybe they're tied, but that makes sure that the average length of these lists can't be too big, at least when you average them out. Okay, we use a random universal hash function such as multiplicative hashing, and we call every table element a bucket. I said it's a chain. Sometimes it's a chain, sometimes we call it a bucket. So what the invariant is that V at hash of key is a singly linked list of pairs where every pair's first element, meaning the key of that pair, is equal to the key that was used for the hash function. And a bucket can be empty. So now that we've defined that structure, let's go through some pseudocode for how this class would work. This isn't exactly C++, it's kind of pseudocode, but we would have a template class where the key type and value type, K and V, are parameters. We'd have our vector of singly linked lists of pairs. We'd have a multiplicative hash function that we use to compute indices, and we'd keep track of n, the size, or the number of pairs. So the constructor would set up the vector with some initial size, I guessed 4 maybe to begin with. An empty vector wouldn't work, so you need at least some size there. So maybe start off with a size of 4, initialize the hash function. You have to tell the hash function what m is, because that was given in that multiplicative hash construction process. Initialize n to 0, and we're fine with the default constructor that sets every singly linked list in the vector to be empty. The size is just return n, so each of those are constant time because they're just initializing elements. Okay, contains. So contains is the map operation that's given a key and tells you Boolean whether the given key exists. So here's what we do. First, we calculate an index from the hash function. So we've got our hash function we call hash.h on key. So that invokes the hash function. The key is mapped into a integer, and that integer goes through that a times c plus b mod p mod m thing. But anyway, what comes out is a valid index in this vector. And then what we have to do is search through that linked list to see if any pair has the right key. So kind of the hard part is calculating the index to look at. That's done on this line of code. Then we loop through this linked list, which often only has 0 or 1 or 2 elements, but still we need a loop to hit every pair. So for every pair p in v of I, if that pair's key is equal to the pair we're looking for, then return true. And if we get all the way through that linked list and never found what we wanted, we return false. So from now on, let's say L is the expected length of a bucket. We're going to analyze that in the next video, but let's say L is how long the bucket is that we loop through. This operation clearly takes big O of L time because calculating the hash code takes constant time. This for loop visits every element in the bucket, so it repeats L times, and there's constant time spent inside the body of the loop, so big O of L time. And we're going to see all of the remaining operations have that same big O of L runtime. Find is a variation of searching where we're given a key and we want to return the pair that holds that key or throw an exception if there's no such thing. It's basically the same process. Calculate the index of the bucket to loop through, and then have a loop that visits every element of that linked list. And if we find a pair that has the key we're looking for, we return a reference to that pair. And if we get through the whole loop, this time we throw an exception. Again, it's constant time to calculate the hash value, and then this loop repeats L times, so it's big O of L time for find. Insert has a similar approach. So if the hash table already contains the key, then we return false and do nothing. And we can use that contains operation we developed 2 slides ago. There's a resizing aspect to this if the size invariant would be violated. So if n is equal to the vector's size, that's m here, then we do a resize. This is just like a vector. We double the size of the array, copy everything over. And then after this statement, we know that the array is big enough, and we calculate the index to use as usual. And at this point, we know that the key is not in that linked list, so we actually don't need to loop through it. We can just add the pair q to the front of vi. And it's a singly linked list, so adding to the front is constant time. So altogether, this thing is big O of L time. The bottleneck is the contains operation, which takes big O of L time. And then this would be amortized constant time, kind of the same thing as adding to a vector. This is a constant time thing. Adding to the front of the linked list is constant. So it's big O of L amortized time. And the amortized tag goes in there due to the occasional resizing, just like a vector. Finally, erase has the same idea as some of the other ones. Check if the key is present or not, and if it's not present, we don't need to do anything, just return false. Otherwise, calculate which index to use as usual, and then have another one of these for loops that visits every single node in the singly linked list, and if we find a pair that matches the one we're looking for, then we erase it out of the linked list. And one property of singly linked lists is that if you have an iterator to a node, you can delete that node in constant time. So again, this is big O of L time. The contains call takes big O of L time. It's constant time to calculate the hash value, and then this for loop repeats L times and spends constant time per iteration. So big O of L time total. So altogether, here's the efficiency of our chained hash table. Many of the operations are defined in terms of L, which is the expected length of a bucket. We need to work that out to complete this analysis. But the constructor takes constant worst case time, and then all of the other operations take big O of L time. So contains and find, those take big O of L time, where L is the length of a bucket. Insert takes big O of L amortized time. The amortized is in there because of occasional resizing, and the erase operation is also big O of L. So if we can get L to be a small number, then this is a very efficient data structure.